All right. We're online. Just have some things over here. No. Quality is good. Stepper motor. DC motor. No, this is a stepper motor. Stepper motor. Servo motor. DC motor. Power supply. I think I need to get one more power extension somewhere quickly. Nothing is really connected there, no. Where does this go? Where's that? It's Pavel's stuff. All right, so let's check this one. Maybe we should enable some mouse tracking. Ta-da. Ta-da, here we go. See you. I wonder, is this still recording? Looks like. The sound is still on. I think it's also 4 o'clock, but we're gonna wait for some time again, like for some 5 minutes. So everybody's late, but I think that today there are not going to be too many people, but it's all right. It's all right. All right. Okay, 3 more minutes, and then I start. Okay. So, welcome to the Fab Academy Thursdays, the lecture series that are here to introduce you to the basics of Fab Academy weekly topics. And this time we are doing a second run of the Introduction to Motors and Arduino session. So last week there were some problems with sound, and other technical problems. And what I have here today is a camera setup where I'm going to show 3 different kinds of motors. So one is going to be the DC motor, so the other one is going to be this servo motor, and the third one is the stepper motor. Then we have here a power supply. Of course, there's an Arduino that we are going to use to control those. In the real Fab Academy setting, you would use something that is based on ATtiny, but next time or next year. Then, yeah, and a breadboard, some jumper cables also nearby. And I am going to start with a brief presentation about all these 3 kinds of motors. To introduce you slowly to the topic and explain the concepts behind it and also the terminology. So let's begin. So here's my presentation. So driving motors with Arduino at the Aalto Fablab in Helsinki. So we are going to look at DC motors, servo motors, and stepper motors today. There are more kinds of motors, but these are the 3 basic ones that you might find useful for your project. Then, so yeah, let's start with DC motors. So DC motors usually have like 2 poles, so plus and minus. So you connect a certain voltage to one of the poles, and then the other pin of the motor you head to the ground. And then once there's a difference in between these voltages and current starts flowing, the DC motor starts to spin in one direction, as you can see in this image. And it's a very simplified diagram of that. Then once you flip the polarity, so once you flip the plus and minus, then the motor usually starts turning in the other direction. Yeah, so you can see that, I mean, if you apply full voltage, then it usually spins at full speed. And what we sometimes would like to do is to control this speed with something. And that we can do with PWM, or pulse-width-modulation. And in simple terms, PWM looks like this. So on the bottom part of the slide, you can see that so there's this wavy diagram. Worry not, it's not that complicated. So there are 2 states that I pointed out there. So the high state, or 5 volts, and the low state, or 0 volts. Basically this is what defines, so this is the way how microcontrollers and computers tell whether something is on or off. So if there is voltage, then it means that it's on or 1. If there's no voltage, then it's 0 or 0. There's off or 0. And then the pulse is defined by the time that a pin or a connection is on. Then there's another concept that is relevant to the pulse-width modulation. It's the duty cycle. So it's kind of it's a window of time which is being measured. It's the full time of pulse and non-pulse together. So the pulse is the time when something is on, and then the rest of the time it should be off. So and this is kind of the full period that is going to be taken into account, and a percentage of this period is the pulse. So yeah, if we try to explain pulse-width modulation, then pulse is the time when the pin is on, and width is the width of the pulse, or how long is it on, and then modulation is when we modulate this width over time. So we make it bigger or smaller in relation to the to the length of the duty cycle, which is usually 250 microseconds, but it can be also longer. In terms of DC motors, you could use that to control the speed of the DC motor. So it's not always successful, but with LEDs it works. I think the last time I tried, the successful duty cycle was not 250 microseconds, but it was 2000 microseconds. However, the next thing that we are going to look at is servo motors. And a servo motor is good because you can control, it doesn't spin continuously, but it spins towards an angle. So you specify a pulse, a length of a pulse, or a width of a pulse, and then according to this width of the pulse, the servo is turning to a specific angle. So as you can see, the duty cycle in terms of servo motors is 20 milliseconds in this case. And then part of these milliseconds defines how far the servo turns. So normally, so by default, I think in most cases it's from 500, or from 500 microseconds up to 2000 microseconds or 2 milliseconds. And then within this range, the servo turns 90 or 180 degrees, really depends on the servo motor. And the third kind of motors that we are going to talk about are stepper motors. And so this is a simplified diagram of what happens within a servo motor. So it consists of stator, which is the electromagnetic part, so which we are going to control with a microcontroller input. Then a rotor, which is usually a magnet, a permanent magnet in the center of the motor itself, and then phases, which define which are there in order to make the motor the step. So you activate phase A and phase B in a sequence in order to make the motor turn. So basically applying a pulse to phases is controlling how the rotor is aligned. And this goes like this. So if we apply a pulse to phase A, let's say, then the rotor changes, aligns with phase A, or with the electromagnet that is connected, that is within the phase A. And then step 2, pulse phase B, rotor aligns with phase B, like so. And then you continue this many times over and over, and then you get your motor to spin. Yeah, so that's with the presentation. So we can actually start doing something. Oh, hello. So you missed the presentation, but I think that's fine. So the first thing that we are going to look at is the DC motor. So this one. So you see it has a very simple layout or design. So it has only 2 wires, so the red and blue. So the red probably is normally supposed to be connected to the plus and the blue to the minus. But as I said earlier, so the polarities can be flipped, and by doing that you can spin it in one and the other direction. So let's see in practice what does it mean. So I'm gonna get rid of these extra things on this here, the other motors. I'm gonna take a breadboard. Don't mind this microchip here. And then I'm going to take an Arduino. And basically the simplest form, the simplest way how we can do something is we can just connect the blue to the ground pin of Arduino here. Blue wire to the ground pin, and the red wire to +5 volts. and as you see, it starts spinning, just like that. But yeah, so our intention is actually to be able to control that. In order to do so, we're gonna connect the motor first to the breadboard, like so. I'm gonna insert the blue cable here and the red cable here. And I'm going to use a few jumper cables in order to connect them to two different digital pins on the Arduino this time. I'm gonna disconnect it first. So I'm gonna connect this yellow part to the plus, to the red wire. Or I'm just gonna choose the same colors of the cable. So the red jumper cable to the red one, and this will go to number 7. And then the blue, let's check the blue one. Where is the blue one? Here we go, there, the blue one. Yeah, so let's connect the blue one to the blue one of the motor, and the other end to pin number 8 on the Arduino, like so. And let's try to write some code for it. So I'm gonna activate the desktop layout here, and we are going to start a new Arduino sketch. I'm going to delete these comments, they are not necessary really here. And we are going to start by defining 2 pins that we are using in our design. So define pin A, which is going to be pin number 7, and define pin B, which is going to be pin number 8, like so. Next thing we have to do, we have to define them as inputs or outputs, and obviously we are going to use them as outputs this time. So for that we use the pin mode command. So for pin A, output, and for pin B, also output, like so. And yeah, and then for a loop we are just going to create a simple sequence where we are going to turn the motor on to spin in one direction. So for that we'll use the digital write command. So we are going to turn pin A high first. So high is the same as 1, or you could also use true in this case. So on and off, it's 1 or 0, or true or false, or high or low. All right, let's stick to high. And pin B to low. So we just need to create a difference in voltages, like so, so that the motor spins in one direction. We're going to do so for 2 seconds. So this is why we use the delay function in order to make a break of 2000 milliseconds. So which equals 2 seconds. And then we are going to stop the motor by turning both of the pins low. I could leave this one out, but just for clarity, I'm also going to pull the pin B low, even though it is low already, like so. And another delay of 2000 milliseconds. And now I'm going to flip the voltages. So pin A is going to be low. And pin B going to be high. And then I think I'm gonna copy this here, and again I'm going to stop for 2 seconds. And at the end of the cycle, I'm also going to stop for 2 seconds, like so. So yeah, all in all, it seems simple enough to be able to almost fit on one page. Maybe like so. It's gonna be easier to oversee all what is happening. So yeah, now we are on one page. Let's try to compile it first to verify if it compiles. We need to save it first. So so this is going to be DC demo. So compiling sketch, done compiling, so no errors. That means that it's all fine. So now I'm going to connect the cable to Arduino. And I'm going to check under tools whether I have the right board selected. So mine is Arduino Genuino Uno, and the port, this should be the port. I'll select that and click on upload. And in my case now, it seems that the motor actually doesn't have enough power. So I think the original way, let's just go a step back and let's change the connections a little bit. So let's connect the ground to the actual ground. Let's just try to switch it on and off just like that. And in this case, we will need only pin 7. Just going to be pin A. Like so. This is going to run for 2 seconds and then stop. Okay, let's connect it back again. And upload. Yes, and now it works. I don't know why it happens. It seems that the motor itself, so even though it's a small motor, it requires a little bit more voltage in order to be driven. And I think it would be decent if you would use some sort of a amplifier in between, like to normally drive it, but for the case of demonstration this is fine. So we are going to use a sort of an amplifier in the following steps. And theoretically you should be able to control speed by using pulse-width-modulation, but it's a really cheap DC motor, and I think it's designed for cases where you just need to spin it in one direction. So yeah, that's that. So this is like really simple demonstration of how to drive a DC motor. I'm gonna disconnect the Arduino now. Yeah, so how about other kinds of motors? So let's get rid of this and let's introduce the stepper motor. No, this is the servo motor, sorry. I'm always forgetting which is which. So this is a servo. So if you remember from the presentation, so with this you can it doesn't continuously spin. It adjusts, so it turns until a certain angle that you control by using a pulse. And yeah, so these pins here on the board. So I'm gonna switch to the clear camera view. this one. So yeah, these pins here I put there in order to connect the so this specific connector here. I'm gonna connect this like so. So you see the orange wire is more to the center of this connector than the red wire and the black wire. So these usually stand for, so black is the ground, red is usually 5 volts, and then the yellow one is usually sort of a signal. So usually you can read that in a data sheet. I'll show you how the data sheet looks like. So here we have a Microsoft Word document. So this is what I found on DigiKey. So DF robot. So DF robot, drive the future. Micro servo motor, which weighs, I don't know, is it like 9 grams, and then it's actually able to lift 1.6 kilograms. Introduction. Do you need a servo for a tiny little project, or you're seeking for an affordable solution? Yes, both. And then applications, insect bot. So we are not really going to make an insect bot today, but we're looking for some specifications for a demo. So what I'm looking for is dead set, 7 microseconds. Yeah, I'm looking for the minimum and maximum pulses that I could use in order to drive it, and yeah, so there are some instructions and all that. But however, so I'm just gonna first try to drive it with the Arduino library. So that's the simplest way how to test the motor. So I'm gonna close this DC motor demo and create a new clean sketch for it. And so the first thing that we need for it is to include the servo library. So which goes like this. So you go to include. So instead of define this time, the first line we use is include. So using libraries is generally not recommended in the Fab Academy, especially if you're dealing with simple things like driving servo motors. But in order to get started and just to test whether your servo motor works, I think it's a good idea to use it. Let's run that H. So that you just get some basic concepts of how it works, and then you can move a small step further to understand how it really works. And we are going to, so we need to specify a pin. So we need a definition. Just going to be pin 9, which is pin 9 on Arduino is like a PWM pin. So if you take a closer look on the board, so you see there's number 9, and I go over here, number 9, and next to the number 9 there's this little tilde character, which means that it's pulse width modulated. So it has a chip supported pulse width modulation thing going on there. And this is why, here we are using pin number 9. And and then we need to create servo object. Like Servo Motor. Servo motor, and we are going to use this motor object in order to attach the motor to a specific pin. We need to let the Arduino know which pin is going to be used for controlling our motor. And then so servo means the type of the object, so it's of a class, and then the class usually has it has to be instantiated, so you need to create a new instance in the memory. And now through this instance we can use the functions or the methods that are defined in this class. So in this case we need to use the attach function in order to attach a specific pin to it. It's going to be the servo pin, like so. And what we can do now, so this servo library, it provides us with a really simple interface how we can control the angle of the servo. So motor dot right, so 0 degrees, and then we can add a delay. Let's say 1 second, so which is 1000 milliseconds. And then let's say 90 degrees, and then again delay of 1 second, like so. Let's try to compile it. Well, first we need to save it. So where did we have the no Arduino here. Okay, so this is going to be servo library demo. Let's go and save. So it's compiling, and it's done compiling, so no error messages, so which is really nice. And now I'm going to switch over to the camera view, and let's connect it to the necessary pins. Like one thing that I'm going to add is also like a little shoulder. So usually these servo motors come with little parts that can be used as connectors to some other parts that you might use together with your servo. So in this case, like this. So you can, if you're building an insect bot, then so probably you would connect this little connector to the parts of the insect, the legs and hands and things like yes, yeah, things like that. So head, or maybe you want to make it eat another insect or some herbs. Yeah, and then the other connections go like so. So as you see, there's this black cable, so we need black jumper cable in order to connect it to the ground. So let's go and connect it to the ground. And yeah, from this side better. So, and then the red we need a red jumper cable in order to connect it to the plus 5 volts. Let's do so. Plus 5 volts. By the way, so if you're interested, I have these motors, and so this time I have a bit more, so you can play around with them. Yeah, also plus 5 volts here, and then we need to connect the orange cable. So let's get a decent orange cable, so we can connect the orange cable to the actual signal pin, which is pin number 9 as we defined in code. So yeah, these are the connections, so you can clearly see. Oh, like so. And then I'm going to connect it to the computer. So then let's put the motor in the middle of the screen, like that. And I'm now going to transition to the desktop and click this upload button. And so it's uploading. Yeah, and it's working. And so yeah, we can change the angles. For example, we can add motor dot right 180, and
See you tomorrow.
see you, and delay another 1 second, like so. And let's hit upload, and let's see what happens. So now it's supposedly moving a full 180 degrees, but as we can see, it's not really the case. So these are really cheap hobby servo motors, and the default library, it doesn't really know, so it's really hard to find out. So there's no information in the datasheet about what are the pulses that are necessary in order to drive it precisely to 0 or 180 degrees. So this is something that you have to find out yourself, and so this is like the very basic testing way how you would test if the motor works, but I will show you the a bit more complicated yet not C programming way how you can modulate the pulses yourself. So I'm going to disconnect it so it doesn't create extra noise. So yeah, that's here we stop. So with this example we stop here. Let's create a new Arduino sketch, like so. And like first things first, we will need some variables. So first of all, we will need to define a servo pin. So let's leave it where it's connected right now. So it's pin number 9. And in this example, we are going to do everything in a setup. So we won't need the loop part. And we are going to define the minimum pulse width, which is 544. So this number is not, I didn't just figure it out, but if you open the servo library on Arduino and you explore the code a little bit, so this was Laude's suggestion, by the way. I wouldn't come up with it myself so easily. So yeah, you can see that there are some constants defined here. So minimum pulse width, which is 544, and maximum pulse width, which is 2400. So let's start with these values in order to, yeah, and a refresh interval in terms of in microseconds, so 20,000. Yeah, so this is how long the servo waits in between the pulses. So every 20,000 microseconds, it kind of refreshes and starts measuring how long is the pulse, and then adjusts the angle according to that. So yeah, let's start with these values. So I'm just going to move away this one. So pulse minimum, and define, just go to 2400. Another thing that I'm going to define is the duty cycle. It's going to be this is going to be 20,000. So if you take off these 3 zeros, then we are left with 20, which then translates to milliseconds. So just we are going to note here that this is in microseconds. not milliseconds. And then in order to make this, so yeah, the reason why I'm not doing it in loop is because I tested earlier, and if you're doing these precise pulse modulations within the loop, Arduino loop cycle, then the timing, you end up with timing that is not that precise. So there should be, yeah, basically these kind of timings you should do on the microcontroller level without using the Arduino library at all. But if you're using Arduino, then I'll show you a way how you can use the setup function in order to do these precise enough measurements so that the motor doesn't shake. So if you do it in the loop, then the motor starts shaking. So it kind of goes to the position and it vibrates a lot, and it's not nice. And I'm going to use a unsigned long data type, which is long enough in order to keep the amount of microseconds that we are going to measure within it. Yeah, maybe this is not necessary. So we need pulse. So this is in microseconds, which is going to be initially pulse max. And then we need also the last measurement in microseconds. So the time when we took the last measurement. So of the measurement of the timer of the integrated circuit, so or of the microcontroller. And in Arduino environment, there's a handy function which is called micros, which gives you a reading of the in microseconds since the boot of the microcontroller. And actually, yeah, I'm still going to go for the duty cycle variable because it's going to be useful in calculations later. So it's, for calculations, it's always good to have the same data types of all the variables that are involved, especially if you're dealing with microcontrollers. Like this. Yeah, and in the setup, so the first thing is what we are going to do. We are going to set the pin mode. Yes?
I would like to take my speaker boxes from the storage.
Maybe you can open the storage then. Okay, the first thing is we are going to set the pin mode of the servo pin to output. Like so. And then we are going to do a trick which normally wouldn't require a setup function at all. It would require a main function. We are going to use an infinite while loop. So while true, or instead of true, you could also use just one. We are going to measure, to get the current time first. In microseconds, like so. And then we are going to compare this time to the pulse. To the pulse length. So basically, while the current microseconds is smaller or equals the last time we took a snapshot of the time, so it's some time in the past. Obviously, if you use only the last snapshot, then it's always going to return false, and it's not going to be true. So we need to add the pulse width in microseconds. So, and as long as the current time is less than last measurement plus the duty cycle, we can write the digital servo pin high. So servo, like so. And then whenever it's not so, we are going to write it low. And then after this, so we are checking if we are within the duty cycle, and if the duty cycle is over, we need to refresh the timer. So if current time is exceeds last measurement plus duty cycle microseconds, then we are actually assigning the last measurement to be current measurement. And yeah, so it might seem complicated, but if you think it through, then it actually makes sense. I will save it here. Oh, that's in the wood workshop. So you go upstairs. There's a in the control room, in the main kind of control room, there's a white rotary switch, and it should go to 1. Yeah, like upstairs. Servo row demo. That's okay. And let's try to verify it. Yes, it compiles, no error. So now I think we are ready to switch over to this view over here. Let's connect it. There's still the old code. So let's just click the upload button. Transition. Yeah, now it just stays in one position. So basically, you just turn to the maximum that we defined in terms of pulse width, and stays there. So in order to change that, we need to add some other variables here that would let us, like according to the millisecond timing, so every 2000 or whatever number of milliseconds, it would maybe randomly figure out an angle, or just toggle between two different angles. But actually randomizing it seems like a good idea, so let's try that. So let's use unsigned long variable. There's going to be our last milliseconds, like so, and you're going to define a delay. In milliseconds, which is going to be, let's say, 3000. And every 3000 milliseconds we are going to do something. And then in this while loop, after we measure this in a similar fashion, we can measure the current. So first we are going to get current milliseconds, which is going to be equal to the millisecond measurement. So we are using the Arduino function millis in order to read how many milliseconds have passed since the boot of the Arduino. And if these current milliseconds are more than last milliseconds plus delay in milliseconds, then we are ready to do something. And in this case, we could assign well, let's just switch it between minimum and maximum values for now. So if the current pulse is max pulse, then you're going to assign the pulse length to minimum, and else we are going to assign it to maximum. So every 3 seconds is going to toggle between the minimum and maximum values. And by using this, we could actually tune the minimum and maximum values in order to match the full 180 degrees precisely. So let's try to do that. So I'm now going to try to verify it. So yeah, there are no errors. So let's try to upload it. Alright, something bad happened. I think I forgot one thing. That after this, I need to set the last milliseconds to the current milliseconds. Like so. Let's try to verify it again and upload. Yes, now we are talking. So you see it kind of doesn't turn completely. So it's not 180 degrees, so we can adjust the values somehow that it is. So I think I'm not going to touch the minimum, but I'm going to more reach into the maximum values. Maybe I'm going to start from 600 here, and I'm also going to change this to 200 and 2600. Let's see what happens then. Yeah, I would like to know which is the maximum, which is the minimum value. I'm going to go for 400 here. Alright, so this is like overshooting probably a little bit. So let's say this is 500. Seems like this could be it. This could be full 180 degrees now. yeah, so this is as close as you can get to raw pulse width modulation with Arduino. Probably there are a bit more complicated methods, but yeah, in terms of timing, somehow this has been proving to be the most reliable method so far. But then the next would be exploring the datasheet of the microcontroller itself, and then trying to use maybe interrupts and trying to do as precise pulse timings as possible. So that's that. Yeah, and the next thing that we are going to try is, I'm going to switch this off. We're going to try to drive this stepper motor over here. Yeah, so these are very good because, so yeah, you would use the stepper motors usually in 3D printers, robotic arms, laser cutters, CNC machines, as opposed to these servo motors that you would use them in measurement devices, or I think they were invented in order, well, what exactly they were invented, but they ended up being anti-missile defense turret drivers. So they would spin this weaponry around in order to shoot down rockets if they are flying in the direction of somebody who's using this anti-missile thing. But yeah, but this is much more interesting because you can build your own CNC machines and robots with it. And it usually requires extra power source, which we are going to use. It's much stronger, also quite precise. So it's quite a revolutionary technology. So whenever you would open up a 3D printer, you would see that in the 3D printer these kind of motors are used everywhere. Yeah, and in order to drive those, you need this external power source. So in my case, I have this 12 volt power source. So you would connect it to the AC current over here, and then you have these two outputs over there, plus and minus, and here you have also a potentiometer that allows you to control the voltage, the output voltage, so it can be a little bit above 12 volts or a bit below, like so. And then as another component, so I'm going to disconnect this servo and the cables for now. As another component, I'm going to use this H-bridge stepper motor driver. And in order to understand how it works, we need to find the datasheet, but no worries. So I have this datasheet over here. So the chip that I'm using is this SN754410 quadruple half H driver. Oh my god, I love these names. And it has everything that you. So this is much more descriptive and clear. So you can here you really can find information. So in this Word stepper, the servo motor Word document, you wouldn't necessarily find all the information you need, but in this one, yes, you finally can. So let's get into it and try to understand how it works. So you see there are some pin numberings. So this little U letter, which specifies the orientation of the chip, 1A, 1Y. I think there was a better drawing about how it works. So you can see all kinds of measurements and predictions, but we don't need to go into so much detail now. So this is nice. Yeah, so this diagram over here, this is what we are looking for. We are going to use pins 1A, 1Y, and 2 and 3 and 4 as well. And the ones that are closer to the ends of the chip, they are marked TTL logic. So this is where we are going to connect our Arduino to. And yeah, if you look carefully at the motor, so you will notice that it has these 4 different cables. And if you remember from the slides in the beginning, so you remember the stepper motors, they usually have these two phases, A and B, and each of the phases, they have plus and minus. So you might ask, so what is the color code? So which is plus and which is minus and which is A and B? No worries. So the stepper motors, they usually also have quite decent data sheets. So we have this one here. So this is the one that we're going to use. And as you see, so each step is 1.8 degrees in an angle. So so which means that, so if you divide, say like 360 by 1.8, so we see that it's actually 200 steps. That's good. So we can do some calculations in the code according to that. And yeah, there's wiring diagram, so it doesn't really have colors, but it has descriptions of colors. So you see that one phase is connected to red and yellow, so this is the first phase, and the other one is gray and green. So red and yellow is going to be 1 and 2, and gray and green is going to be 3 and 4. So yeah, and we are going to connect those. So the motor itself, we are going to connect to the internal ones, because where this 1 ampere, where there's the label 1 ampere, that means that it's, so these pins are enabled to provide quite a lot of current. So these are going to give 1 ampere. But then where does the 1 ampere come from? So no worries, it's all sorted. So it's here's a pin that is marked VCC2, and you can pipe in 5 to 36 volts in here. So this capacitor here, for demonstration purposes, I'm not going to use it, but in order to stabilize the current, it's probably a good idea to have those. And then you also need to provide the reference voltage for the for the TTL logic part, which is 5 volts. So this is going to be connected to the Arduino. And then this VCC2, pin number 8, is going to be connected to the power source. And the grounds of those two, so the ground of Arduino and the ground of the power supply, they should be connected together. And we are going to use this middle part of the chip in order to do so. So let's get started. So from this data sheet, so let's start looking for the cables. So I'm going to switch over to the camera view here. So we need to start with the red and yellow. So let's look for the red cable. So red cable we have already. Here we go, red, yellow, yellow, ta-da. And then we need gray. Gray cable, where are you? Where are you, gray cable? Okay, so gray cable also here, and lastly we need the green cable, which is over here. Green cable, yes. And let's start by connecting it to the Arduino digital pins. I'll just start from 2 and go up. So red is going to be at the number 2 pin. Maybe this is not the best red. Number 2. Then we need yellow to number 3 here, and gray is gonna be 4. And oh, what happened with the green one? I need another green one. And green is going to go to number 5, like so. And in this case, we are not going to take into account whether the pins are PWM or no, because we are going to trigger them manually or software-wise. We're not going to use the PWM feature of Arduino. So let's go and connect this up to the microcontroller. No, the microcontroller with the chip. And if we look at the data sheet again, here. So we are going to connect number 1 to pin 2, number 2, so the second pin to number 7, then to 10 and to 15. So let's get going. Yeah. So if you look carefully, then you see this little U letter that symbolizes, not that it tells us about the alignment of the chip, is up there. So the first pin is going to be the second one from the top left. So this is where we are going to connect the red one, like so. Then the yellow one goes to the second from the bottom left over here. And then the gray one goes over here, and the green goes over there. So like so. Is it correct? Yeah, it looks like. This is how it goes. And yeah, so the top right we need to connect. So I'll switch back to the view over here. So to the top right. The top right should be connected to 5 volts from the Arduino. So for that I'm going to use an orange cable just to make it different. So here, top left, plus 5 volts Arduino, and the power supply over here. So we are going to connect the plus 5 volts of the power supply over here to the bottom left. Yeah, I'm gonna leave some distance so we can see what cables go where. And finally the motor. So let's start with a red cable that goes just next to the red cable from the Arduino. So the yellow goes to the yellow, and the Arduino over here, and then the gray one goes next to the gray one, and the green one goes next to the green one over here, like so. So now we have all the connections ready. So I'm not going to connect the power supply power outlet yet, so before I get the code right. So this is disconnected, so it's free. So in order not to burn the chip and not to burn the motor. So the first things first, I'm going to write some code. So let's create a new Arduino sketch. I'll close the old one, move in a new one. I'll delete the comments. And let's start out by defining the pins where we connected. So start with motor pin 1, which is going to be 2. As we remember, we connected it on the pin 2 on Arduino. So starting here from the digital pin start. So and then define M2, which is going to be 3, pin 3. Define motor pin 3, which is pin 4 in our case. Define M4, which is number 5. And so we need to know number of steps, which we remember we did a calculation is 200, and we need also to delay of the steps in microseconds. So it's going to be 25,000 microseconds, or 2.5 milliseconds. And we need also the length of the full cycle. So this delay step US microseconds, it's the length of the pulse that we need to give to so in this is the pulse width that we need to have there in between the steps. And by controlling this, we can actually control the speed of the stepper motor. This one was delay cycle in milliseconds, and this is going to be kind of a delay after each full revolution. So 2.5 seconds, or let's set it to, in order to make it different and more clear, I'll set it to 3 seconds. And in the setup, we need to start to set up the pins. So as outputs. So we can copy this because we just need to change the number, M2, M3, M4. And we need to also pull all of them low so that it stands still. And we can copy this as well and just change the numbers for the motor pins. And here we are going to use the loop, although for precise timing it probably would be a much better idea not to. But here it doesn't matter for now. So we are going to start out with a counter. I'm not going to use a for loop here. I'm going to use while loop for clarity. So this is going to be the step counter. Or yeah, just counter. And while the counter is less than number of steps divided by 4. Divided by 4 because we are actually going to go 4 steps at a time in the while loop. It's just this is why I divide the number of steps. So we're actually going to have 50 while loops because we are dividing the whole step count into with 4. And yeah, it goes like this. That first, for the first phase, so we just apply voltage to the first phase, and this we do by pulling one of the pins high, so the first pin high and the second pin low. And then the second phase we are going to deactivate completely, so we are going to remove voltage from it at all. So M3 is going to be low, and M4 as well, like so. And then we are going to wait for delay in microseconds. So this is the number that controls the speed of steps. So the smaller the number, the faster the stepper motor moves. And now we can copy this block and paste it below. And this time we are going to activate the second phase, or the phase that is between M3 and M4. Like so. And then for the 2 other steps, we are going to activate the things in between. So we are going to activate the third pin. And then for the 4th step, we are going to activate the last pin. Like so. And then just after this is finished, we need to increase the counter. And by the way, it's the same as if you would say counter plus plus or counter plus equals 1. But I think this is the most obvious way for you to understand how values are being added to the same variable. So you can reuse the same variable name and you can just add one to it and assign it to itself, like so. And then after this longer while loop, we can use the regular delay command. In microseconds, and if you look above, so we set this to 3000 milliseconds, which is 3 seconds. And let's try to, yeah, we need to save it. Stepper demo. Let's verify. Okay, so no errors. And so yeah, let's try to connect it. So here, of course nothing happens because we haven't connected it to the power supply. And we can upload the code. Yeah, so it's done uploading. And now let's try to connect it to power supply. So I'm gonna plug this in somewhere here. Sorry. Can I get it closer? Oh no. But it's fine. I'll connect it later. And yeah, so there's one last thing missing in our design. That is that we haven't connected the grounds. So I'll disconnect the power supply for one moment once more. So here, as you see, this ground is floating. And in order for it to work, we need to connect it to one of the pins in the center of the chip. So if we examine the data sheet again, here we see that these 4 pins in the middle, they're for the ground, for all the grounds. So for the grounds, so these are all connected, and we need to connect the ground from the power supply with the ground of the Arduino over here. So for that, I'm gonna get another black cable. So I just connected the power supply ground, and let's connect the Arduino ground over here, and let's plug it in now. Yeah, as you see, it does one full revolution, and then it stops for 3 seconds. So yeah, and if you want it to spin in the other direction, then what you have to do is we have to copy this while loop, and before the second while loop we need to reinstantiate the to 0, so we need to set it to 0 again, and we need to do things in the opposite order. So we need to start from the bottom one, and then this one, and then in a similar fashion, like so, and then the first one as the last. Just kind of flip the pulses, and then yeah, after we make these 4 steps, consecutive steps, we again increase the counter, and then we have a delay. I'll copy this delay and put it in between the while loops over here, so make it more clear. Let's compile it. So yeah, if you cannot follow the code, don't worry. I'm gonna upload it to the GitHub repository of Aalto Fablab, and you'll be able to download it and check it and try it out yourself. So the images and the layouts you can get from the video, but maybe it makes sense to add some screenshots. That will do. I'll try to do as well, with code primarily, and the link to the code I will add also to the description of the video. So no worries. So let's try to upload this one. And, yeah, so you see it's going in one direction and then in the other one. And maybe let's try to experiment with the speed a little bit. So let's make the interval between steps 1500 microseconds and the delay between cycles 1 second. And let's try to upload it. Yeah, it's much faster now. And of course you can use the Arduino stepper motor driver, but I think it's much more fun if you try to kind of understand how it works in a pulse level. So in terms of Fab Academy, it's very useful because you will probably do it on a pulse level by using 80tiny 44 or 84 or 85 or 45. Yeah, driving simple things by using the pulse level, pulse-width-modulation. I think it's smart because like these chips, they don't have so much memory. But then if you are building a machine, then probably you would like to use like a proper motor driver, which is community tested and has undergone many iterations of development. But it's always nicer to understand how things work, in the lower layers. Yeah, so this is it for now. I hope you enjoyed it, and next week I'm still going to figure out what we are going to do. But maybe since I missed to document or to record the HTML session or Git session, so I could do session about Git version control, for example. If not that, then maybe a rerun of how to design tool paths for the CNC machine by using Fusion 360. Or I actually have to prepare some things for water jet cutting in the Fusion 360 sheet metal workspace. So maybe a tutorial about that. But yeah, let's see how it goes. If you're watching this, and if you are, I don't think that there are too many people watching, to be honest, but if you have ideas, just feel free to post them. Otherwise, thanks for watching and bye.